Welcome to EDU World Space.
We're asked to use direct integration to calculate the mass moment about the x-axis here of this tetrahedron, and this is a really ugly problem, and hopefully this wasn't assigned for homework because it takes forever. So what we need to do is we need to look at each of these, so we can think of this tetrahedron as a bunch of stacked up little triangle slices or wedges. Okay, and so we'll stack them all up, and then we're going to integrate them all, and so we can find the mass moment of each of them about this axis. So to do that, we need to use the parallel axis theorem for the differential element. So we know the sides, or the distance here and the distance here are both functions of y. So the sides of our triangle go like these, okay? Because this has a length b, and this has a length a, and then down here at y equals minus h, we have that they both become 0. Well, we can then say, well, what is our differential area? The differential mass moment of one of these little triangular slices about its center of mass. So about its center of mass, we can use the area moment times rho times the thickness, and the thickness is just going to be our differential element dy. So the area moment is 1 over 36 times the base times the height cubed. So we get z1 cubed, this function cubed, times x. So this function. So then we can substitute all of this, and this all becomes a function of y. Now, the problem is we need to find the mass moment of each one of these little triangular slices, not about its own centroid, but about this x-axis. And so we need to use the parallel axis theorem to go from here to here. And that obviously also depends on y. So about the centroid, we have this value from up here. And so then we need to use the parallel axis theorem. And so we have the mass is rho a. And then d squared is the distance from the centroid of the differential triangle that we're looking at to the x-axis. A is obviously a function of y where we are, so that's z1, or 1/2 z1 times x1. Okay? So that's a function of y. The distance here squared, we need it squared, so it's this distance squared, which is z1 over 3, plus this distance squared, and that distance is just y. So we have this piece and this piece. We have all of this stuff. Now we have all of this stuff in terms of a function of y, which then we can start plugging things in, and we need to integrate from y goes from minus h to 0 of all of these little differential triangular wedges or triangular plates. And we have everything in here. Again, this is the whole thing written out. I haven't plugged in all of our functions from over here, but everything in here is a function of y. And so we can multiply it all out and crank through all the calculus, and half hour later we wind up with a fairly simple answer here, and that is that j about x is abh over 60 times the density times b squared plus h squared. And now if we want to get at that in terms of the mass, we need to find the volume of this, and you could either look up the volume of a tetrahedron, or again integrate all of these little triangular wedges up from minus h to 0. And each of those triangular wedges has an area of 1/2 z1 x1, and this is a function of y. And if we crank through that, we get ABH over 6. So after many minutes, we can substitute rho is m over v, and then we just get that the mass moment about the x-axis is m over 10 times b squared plus h squared. Okay, so that would be if we were trying to rotate this thing about this axis, the inertial resistance to trying to accelerate it about that axis. And it makes some sense because we can see that it depends on h squared. Again, how far down here it is, how tall it is, and b squared. Notice here A doesn't show up in here, but A obviously appears in the mass if the density is uniform, and so we can see here that the mass moment scales linearly with A if we use just the density here. So obviously A depends on it, and again, as this thing gets wider, the mass moment would grow, but it would grow just because the mass is getting larger.